So relative motion has just a couple of quick definition terms. It has a frame of reference, so it's a coordinate system relative to which a motion can be observed. And it also has a relative velocity, which is a velocity of a body relative to a particular frame of reference. So basically, if you let's say are standing on the highway, you're just standing on the side and cars are passing by. Your speed relative to yourself is 0. And then the car approaching you is then going whatever speed it might be going at, whether it be 100, 110 kilometers an hour. Now, let's say, for instance, that you're running with the traffic. So as traffic's going ahead, and that means that you're running at, let's say, like, 2 or 3 kilometers an hour, for instance. Like, it's just a light walk, a jog. So even as you're increasing your speed as you're moving along, when you look back at the cars coming at you, they actually will appear slightly slower because you're traveling a certain speed relative to the speed that's already coming at you. So relativity really places you in your view on how the world exists, how other things happen. So, for instance, I mentioned earlier in one of the first videos about the speed of the planet as it's spinning around its axis. We don't feel that, right? We don't feel the planet rotating around, even though we know that it does a certain cycle in 24 hours. But if we could stand ourselves outside of the Earth, we would see that the Earth is moving quite quickly. And so, based on our relative perspective, you really get a sense of how fast things are actually going. So, a couple of just kind of quick things with this one before we wrap up. So suppose a cruise ship's moving 5 meters per second south relative to the coast, and a passenger's jogging at a velocity of 3 meters per second south relative to the cruise ship. So relative to the coast, how fast is the passenger going? So to understand this or to visualize this, really we should probably sketch a little picture. So let's say that you have your coast, and there's somebody standing on the coast that's kind of watching this whole thing happen. And so the cruise ship, and I'm no artist by the way, so go easy on me, the cruise ship here is moving, heading south it says, and it's going south at 5 meters per second. And then on that cruise ship there's a passenger, and the passenger is traveling, moving downward at 3 meters per second. So relative to this person over here, how fast does it look like the passenger's traveling? Well, from their perspective, both these things are heading in the same direction. So what it actually looks like, add on the direction, so what this actually looks like from the coast perspective, from the person over on the side just kind of visualizing this whole scenario play out, is it looks like they're moving together, right? And so we've actually done this before when we did vectors in a single plane. So really what we have here is we have our resultant velocity is just equal to the velocity of our first event plus the velocity of our second event, because they're traveling in the same direction. So our resultant velocity is really just 5 meters per second traveling south, and normally we consider south to be our negative, so if we put a negative in the front there, plus an extra 3 meters per second traveling south for our passenger because they're heading in the same direction, so we can really see that our resultant velocity is really just traveling at negative 8 meters per second, or what we can say is they're traveling at 8 meters per second heading south. So whenever you're reporting things with directions, try to keep in mind that negatives really just imply that you're heading in a down or a left direction if we consider a south and west to be negative. So a way that I can visualize this, and some people ask in some years, well, does that mean that the negative 8 meters per second is heading north? And the answer is yes. But I wouldn't want you to report this as an answer, negative 8 meters per second north, because we're dealing with a magnitude and a direction, and magnitudes are always positive. So we always have to make sure that we give ourselves the correct direction that goes along with the correct sign. So 8 meters per second heading south would do that trick. So heading in the same direction from the coast perspective from the person, they're seeing this person on the cruise ship look like they're traveling faster than the boat's moving because they're running at an additional speed to what the speed of the boat is already going in the same direction. So then the last question is then saying, okay, well, what happens if, say, that person now on that cruise ship is now traveling, so let's say that person on the cruise ship, this ship's going at 5 meters per second south, and let's say that this other person now is going 3 meters per second, but they're not going with it now, they're going against it. So they're going at 3 meters per second here, but they're heading east. So now, because this is in separate directions, what I have here is a two-dimensional problem. And so relative to the coast, right, what is this person going to see as this boat passes by? And so if I were to sketch this out tip to tail like we talked about in one of the other videos, all it means is where one arrow finishes, the other arrow can start. So if I sketch this out the way that it would go, this person's running 3 meters per second heading east, and then the cruise ship is going at 5 meters per second heading south. From the coast perspective, this is what they see. So from the coast perspective, from our person over here, it kind of looks like the person on the cruise ship is getting further away from them, but also traveling south. So they're moving south of east as they move away. And so then we can figure out, it says determine the jogger's velocity relative to the coast. So then we can figure out what that resultant velocity is going to look like. And because it's a two-dimensional problem, we've been dealing with those, we know how to solve this. So we start off with a little bit of Pythagorean theorem. So we'll do c squared equals a squared plus b squared. C squared is equal to 3.0 meters per second plus 5.0 meters per second squared for each one. C squared is equal to 9.0 meters squared per second squared. So remember, the squared term squares everything inside those brackets. Plus 25.0 meters per second, meters squared per second squared. C squared is equal to 34.0 meters squared per second squared. And then if I take the square root of that at the end, I'm getting 5.8 meters per second. So following our significant digits through this whole thing again, we have 2 in the first one, which means 2 when they're squared. I have 2 with the 5, which means I'll have 2 with the 25 when it's squared. The 9 goes to the 10th place, the 25 goes to the 1's place when they're being added together. That means I can only go to the 1's place when I add them. 2 significant digits there, so when I square root, 2 my answer. So now, if I want to go through and write the angle and find that, then I can put everything together. So tan, I'm going to have to set that down. So tan of theta is equal to opposite over hypotenuse, opposite over adjacent. And if I look at my triangle, remember the angle is always from where you start, so from the beginning of the arrows. And my opposite looks like it's 5 meters per second. My adjacent is the 3 meters per second. So theta is equal to tan inverse of 5 over 3. So 5.0 meters per second over 3.0 meters per second. Theta is equal to, and then I need to do second function tan of 5 divided by 3. So make sure that your calculator's in degrees. And it looks like we're getting 59 degrees. And direction looks like it's south of east. So it's 59 degrees south of the east direction. So if I want to put everything together, the resultant displacement for this thing, resultant velocity is going to work out to be 5.8 meters per second at 59 degrees south of east. Now, a common problem to this, or a common question that people sometimes have, is, well, what happens if we were way back up at the top? What happens if you draw your triangle a different way? Right? What happens if I drew it going down first and then over, and then I had this, where this is 5 still, or sorry, this is 3. Okay, where this is 3 meters per second still, and this one is your 5 meters per second. So if you notice the velocity lines, the resultant velocities, they're the same line, same direction and everything. So this part, the 5.8 meters per second, that's not going to change. What will happen when you get down to tan down here and start working on this part is that really what you'll have is 3 over 5 instead, and that should actually end up giving you 31 degrees. But then when you take a look at your measurements here are east of south. So you could end up getting an answer of 31 degrees going east of south, which is also correct. And really, by the time we take a look at both of these triangles and match them up together, because they're the exact same line for VR, these two angles that we found as an answer should always add up to 90 degrees because it's a right angle in the end. So you don't have to worry about how you're drawing your triangles. I'll have that part figured out for you to have both answers, so you know that you're on the right track. And as well, to know that you're not going to do it incorrectly just because you drew a triangle a different way. So with all that, I guess now you're ready for the next section. So good luck.